Number 56 we did in class, so I'm not going to go into that one again. So let's move on to the next problem, which is number 59. Number 59, and now we're moving into the graphical analysis. And in order to do these, I'm going to try the best I can to draw these so that so I can show you how this works. It says, by taking the slope of the curve of figure 2.60, verify that the velocity of the jet car is 115 meters per second at 20 seconds. Actually, we did this problem in class as well, so I'm not going to go over this one either, except to go over part B. So 59, part B, if we, first of all, and we graph the velocity time curve, and you remember that in class I got actually 120 where they got 115. So if we do that, we take the velocity time curve, and at time 0, the velocity was 15. Time 5 seconds, it was 40. At time 10 seconds, it was 65. And you draw a line, and actually it ends up being a straight line. And so the acceleration is equal to the slope of this straight line. And so what you do, again, so acceleration is going to equal the rise divided by the run, which is v over t. And the calculation here was between 25 seconds and 10 seconds. And from the graph, 10 seconds was 65 meters per second, and 25 was 140. So 140 minus 65, and it's going to be a positive acceleration because the graph is a positive graph. So A is 85 divided by 15, and 85 divided by 15 is 5 meters per second. 75 divided by 15, per second squared. As it turns out, we were supposed to show, by taking the slope at any point, we were supposed to verify that the acceleration was 5 meters per second, and that's exactly what we did. Now 61, take the slope of the curve to verify the velocity at time 30 is 238 meters per second. Now, I actually, again, I didn't actually get that answer. If you look, and it all has to do with how, if you have time is equal to 30, and you have to have your book out and look at this, but y, when time is equal to 30, at least to my eye, is about 9. At 20, y looks like it's about 7.5, and at 40, it looks like at t is equal to 40, let me do a better job here on this one. At t is equal to 40, y to me looks like approximately 12.5. So I took a rise over run, and I subtracted 12.5 and 7.5 because that included the point at 30, and I thought it was pretty much a straight line there. And if I divide that by the 20 seconds, I actually get 0.25 meters per second. I guess 250 in the proper units, 250 meters per second instead of 238. Which again, up here I got 120 and the answer was 115. Down here I get 250, the answer is 238. You know, that's within the realm of error given the ability to read these graphs. Okay, let's look at 64. Take the slope of the curve to find a jogger's velocity at time 2.5 seconds, and then repeat at time 7.5 seconds. And it must be consistent with the other graph. Well, if you look at, first, if you look at the position, the time versus the position graph, and you can see that it goes from 0 to 20 over the first 5 seconds, then it goes back down to 0 or close to 0, and stays pretty close to 0 until you get to 15, and then it goes back up at 20. So at time 0, you're 0. At time 2.5, you're at 10. At time 5, you're at almost 20. It says 17.5 in the answer book. At time 7.5, you're back down to 10. And at time 10, you're at 2.5. And the question was, take the slope of the curve at 2.5. Well, between 0 and 5, it's pretty close to a straight line. And so the slope here is going to be about the rise over the run. You could use, say, 17.5 minus 0 over 10, or excuse me, over 5, and use that, and you would get 3.7 meters per second. And that incorporates and assumes that that's fairly close to a straight line, and that's about the best you can do. And then the second part of the question is to repeat it at 7.5. Well, going from 2.5 to 7.5, you actually peak and then come back down. But at 7.5, it's going down the same approximate rate that it's going up. So just looking at the graph, you would guess that it's about that. But if you were going to put numbers in, you would put 2.5 minus 17.5 over 5 again, and you would actually get 3.0. Although looking at the graph, they look like they're almost the same slope. And then it says these have to be consistent with this, the other graph. And I think they are fairly within the realm of error. If you look at 5 seconds, it looks like it's about 3.7. If you look at 7.5 seconds, it looks like it's about 3. So it's reasonable. The numbers in the table are a little bit different than that. Again, I would say that's because of the changes in or making estimates. Number 65, it says a graph VT shown for a world-class track sprint 100-meter race. See figure 2.68. What is his average velocity for the first 4 seconds? And what is the instantaneous velocity at 5 seconds? What is his average acceleration between 0 and 4 seconds? And what is the time for the race? Now, if you graph this out, if you graph number 65 out, it's going to look something like this. Again, excuse the less than, I don't have any, well, actually, I actually might have a way to do this. Let me take a look. How to change this. I thought I could potentially change this to graph paper, but I right now can't seem to figure out how to do that. Let me look at this for just, yeah. Nope, that's not going to be it either. So I can't really change this to graph paper right now. So I'll just freehand it the best I can. But if you take and you do a graph And this is going to be 2, 4, 6, 8, 10 seconds. And you start at 0 and you calculate the velocity change over the first 4 seconds. Up here at this top is going to be 12. And at 4 seconds is where you make it to 12 meters per second. And it's a straight line up to that point, and then it flattens out after that. There's no acceleration at that. So the first 12 seconds, the average velocity, actually based on this graph, no, that's right. The average velocity is 6 meters per second, because this is a velocity, not a displacement. This is time. So this is 12. So the average is 0 to 12, and it's divided by 2. So it's 6 meters per second. At 5 seconds, so at this point, the velocity is, at this point, right here where it flattens out, the velocity is 12 meters per second. And then the acceleration is the rise over the run of this graph, which is going to be 12 divided by 4, or 3 meters per second squared, up to 4 seconds. And then after that, there's no acceleration because it flattens out. And then the last question is to calculate the distance this person ends up traveling. And so you first start out, for the first 4 seconds, the distance is going to be, V0 doesn't take into account, so it's going to be 1/2 AT squared. For the first 4 seconds, that's going to be 1/2 times 3 times 4 squared, or 16. So that's 1/2 times 16 is 8 times 4 is 24. And then the rest of the race, the distance is going to be VT from 4 to the end of the race. And 4 to the end of the race, that's going to be 100 meters. If you subtract 24 from 100, you get 76 meters. So you've got 12T is equal to 76. So the rest of the race is in 6. It's going to be 76 divided by 12, which is about 6.3 seconds. So the total time for the race is going to be 4 plus 6.3, or 10.3 seconds. The last problem, number 66, I think I showed you in class, and the time velocity curve looks like this, where this is 0, and you start out with an instantaneous velocity of approximately 1, and that goes on until you get to 2 seconds, and then it instantly turns around and drops down to -5. So this is instantaneous 1, this is -5 meters per second, and it stays at -5 for a second, and then it goes up to 0. There's no acceleration, and then it does that from 3 seconds until 5 seconds, and then it jumps back up to 1 for another second to 6 seconds, and then it's the end. So it looks something like this. Now the acceleration curve, at this point, you got if this is the 0 point again, you have no acceleration because it's flat for the first second, and then instantaneously you have a negative acceleration from 1 to -6, so it goes instantaneously to 1 to -6, and then no acceleration, and then instantaneously it goes up a total of 0 to +6, and then comes back, and then there's nothing until 5 seconds, where it goes 1, and then at 6 seconds, it slows back down, and it looks like that. And so, as I said before, I would not put graphical problems in